Welcome to part 1 of the routing series. In this series, we'll explore the role routers play in computer networking, as well as the related technologies that help them function. Now, as you'll remember from the switching series, switching mostly had to do with how we move data around a local area network, or a LAN, and routers are mostly concerned with how we move data beyond those individual LANs. And this can be both inter-VLAN, meaning that you're communicating between VLANs in a local site, or it can be site-to-site, which I've cleverly shortened here, and dealing with communications maybe between a branch office and a headquarters or something similar. As well as we'll look at what happens when somebody wants to use a service out on the internet, like perform a search at google.com or something. Now, the primary way we move this data around between the different LANs and sites and what have you is using IP addresses, and IP standing for Internet Protocol. And IP addresses are similar to MAC addresses in the function in that packets will use them as the source and destination to help the packet navigate the network. But unlike the MAC tables used in switches, routing tables are pre-populated by the network engineer. And as we'll see, populating these routing tables are a large part of our bread and butter. Now, if there's one thing network engineers are fond of, it's keeping everything in a nice, tight, logical order. And the way we do that for IP addresses is using subnets. Now, subnets are just a way to logically group IP addresses together so that we can get the most efficient use out of the space provided. Now, in order to understand how this works, we first need to look at how IP addresses are composed. And so, to start off with, we'll say that they're a 32-bit string represented by 4 8-bit octets. So as you can tell, we're already going to get to delve into the exciting land of binary conversion to really understand these things. But before we go too deep, let's look at what that means. So that there's 4 octets means we're going to have 4 different numbers. Now, when we write it all down, we can make it really nice looking and easy to read. So an IP address might come out looking like something like 192.168.12.1 or something of that nature. When in reality, when we're working with these, we need to convert them to binary. So we're going to convert each 8-bit string into, or each string rather, into decimal string into an 8-bit binary number. So hopefully you've been brushing up since the binary video. So this one's an easy gimme. We know this will be a 1 and a bunch of zeros and so on. Now, what we'll do with this is at some point in the IP address, we'll divide it into 2 sections. And those 2 sections are going to be the network and the host sections. And these will tell the router that's processing the IP address what relevant information it needs to know in terms of where this particular address is. And we tell the router where this division exists using the subnet mask, which we will cover in the next video. So now that I've got you all excited about IP addressing and subnet masking, let's move on to a basic routing example. So here we see a basic 3-router network, and as I mentioned earlier, unlike switches which learn all the destinations as they go along, routers are very stubborn, and when they start out with no configuration, they refuse to communicate, mostly because they don't know how. And so it's our job to come in here and define how they're supposed to talk to each other and what's where and everything else. So we'll start by naming these routers A, B, and C. And just to keep things simple, rather than go into using full-blown IP addresses right away, I'm going to go ahead and stick with naming the IP addresses as letters. And so We'll IP each interface, so each router has two interfaces, so we'll IP the interfaces on router A as IP A and IP B, and B gets C and D, and C gets E and F. Now we'll drop an example of A's routing table. And by default, once you do configure the interfaces, it's going to know a few pieces of information here. And it's going to know the two IP addresses that it's been configured with locally. So it's going to know A, and it's going to know B. And then, through the magic of subnet masking, it's going to know all the IP addresses that are on this link. And so, as a result, router A is also going to know that IPC exists somewhere in IPA's neighborhood, that they're in the same subnet. And the same thing is going to happen over here between B and F. And so, just by configuring these two interfaces with IP addresses and subnet masks, we've already begun to populate the routing table. Next, we're going to mix it up and throw some LANs in the mix. So let's say that we've got a user LAN here hanging off of A, and they want to talk to a server LAN, or subnet as we might start calling it as we enter the wide world of IPs. And again, we're going to have to tell A how to get there. And one of the most basic ways for us to do that is using what's called static routing. And the static part, as you might guess, means that it's a fixed configuration. And the reason that's important is because later we get to learn the super awesome art of dynamic routing, using protocols such as OSPF and BGP to learn how to have the routers sort of automatically figure out where everything is once a few basic configurations are performed. But we won't get too far ahead of ourselves here, and so we'll discuss the static routes. So what we'll do is, on A, we would go in and put a configuration that says to get to the server LAN, you're going to go to your next hop, so we always think about just the next step. So we're just trying to tell A where to go. And really, A has two choices. It can send, well, three. A can send traffic over its link to B via B's IP address of C, or A can send over to router C via C's IP address of F, or it can send the data locally into the user LAN. So in this case, our shortest path here is going to lead us to router B via IPC here. So we're going to tell A, when you need to get to the server LAN, you go to send the packets to IP address C. And it already knows where C is, and so because we've already established this relationship here, it's able to understand this part as well. So we've established a chain or a pathway or a route, if you will, to the server LAN. Now another thing to bear in mind is that as we install these routes, both static and dynamic, we can also assign them a priority. And so what we can do is we can tell router A, that an alternate path to the server LAN is to take this link here via C, and we would then tell router A to send the packets to IP address F instead. Now we're assuming then that C would have a static route entry saying to get to the server LAN, it needs to go to IP address D here. And then we would simply assign, again, a priority or a metric, or there's a number of different ways that this is phrased and works out, which we'll discuss in detail as we look at the different protocols. But as a general rule of thumb, we would probably give C a lower preference, so we'd give it a preference of 5, and F a preference of 10. So whenever the link here between A and B is active, it's always going to choose this route. But if this link were to go down, then this backup route is still available to allow traffic from the users to get to the server LAN. Now, one last concept I'd like to point out before we wrap up part one here is I'd like you to start thinking about the difference between the kinds of links that exist on routers. For example, I would call these LANs that are composed of endpoints such as users or servers or what have you, probably endpoint LANs or subnets. And I say this only to make the distinction between the links such as this one, that all they do is interconnect the routers and allow data to flow between routers, ultimately getting to the different endpoints. And I would call these transit links. So to recap, in this video we discussed the basics of IP addresses and subnets, and also looked at the basics of IP routing. Thank you for watching, and we'll see you in the next video.